In section 10.3, we're going to work with defining and using probability. In our previous two sections, we were working with ways of counting up groups. How many outcomes could you have through permutations or through combinations? And remember that permutations dealt with if I want to be figuring out how many ways I can pull a group together where order is important, I would be working with permutation. And if I didn't care about the order, I would be working with the combination. So now we're going to end up using some of those permutation combinations as a way of helping us come up with favorable outcomes or possibly total outcomes for a given probability problem. So what probability is, it's a number from 0 to 1, can be a decimal, could be written as a fraction, could be written as a percentage as well. It indicates the likelihood that an event will occur. And there are a couple different types of probability, and today in section 10.3 we're going to look at two types. We're going to look at a theoretical probability, and then an experimental probability, and then we'll also be looking at another way of looking at the chances of an event occurring through what we call odds. So theoretical probability, when we have equally likely outcomes, such as tossing a coin, you have equally likely outcome of landing on a heads as you would a tail, for example. Then you have the possibility of theoretical probability being used. We'll also talk about how you could also maybe use odds when you have equally likely outcomes. But here is our breakdown of what theoretical probability is. It's the number of outcomes in an event, some event A, whatever that might be, maybe like landing on heads, over the total number of possibilities. In this case, landing on heads would be one event, and then total number of ways that a coin can land, two events, and a 1 in 2 chance of landing on a head or a tail. And then there's a little Venn diagram showing you in the rectangle here is all the possible outcomes, and then event A, whatever that might be, here we see the oval, darker blue oval there, the 3 outcomes that I desire, so 3 over 8 would be the probability of that event occurring. All right. Let's talk about some examples from a deck of cards. We're going to pick from a standard deck, which has 52 cards, 4 suits. Here are the breakdowns of each of the suits, the types of cards that are in each suit. And we want to find the probability of these 3 different conditions here. What is the probability of me picking a red card? So I got 52 cards out on the table, they're all face down, and I want to pick a red one. So my event A in this case would be picking a red. So my probability of getting a red is going to be equal to the number of ways that I can pick a red now, that's my event that I want, getting red. And then now I have the total number of cards. There's my probability of picking red. So we set this thing up, and I have how many red cards? I have 2 suits, each with 13. Oh, I want a red king, sorry. Red king. So I have 2 suits that are red. A heart and a diamond. There are my 2 red kings. And I have 2 possible red kings out of 52 possible cards, or a 1 in 26 chance of pulling a red king. And we'll take our fractions and we'll reduce them. You can go ahead and make them decimal equivalents if you want to also. All right, how about picking an 8? So again, probability of picking an 8. Probability of getting an 8 equals the number of 8s over the total number of cards. And we have 4 8s out of the 52 for a 1 in 13 chance of pulling an 8. How about a diamond? Probability of a diamond would be equal to the number of diamonds 13 diamonds out of the 52 gives me a 1 in 4 chance that I would pick a diamond out of the deck. So that's simple probability theoretical. In this next example, cereal companies putting 5 new cereals on the market. They include a variety of wheat, corn, rice, oats, and multigrain. The order of the cereals does not matter, and each cereal has a different cost. So, find the probability of the following situation. So, one of the things that is noted here in the statement is that the order of our cereals isn't a key thing, not important here. So, going back to our previous two sections, we looked at permutations and combinations. Permutations would say order is important. Combinations say order is not important here. So just we're keeping that in mind as we come to some more problems throughout the section here. Specifically in the homework, we get some situations where I might be using a permutation and a combination for probability. All right, so probability of ordering the cereal in terms of cost. Now that could be, I can go from highest cost to lowest cost or low to high. It doesn't matter. But we're going to order it in terms of the cost. And if we think about our number of ways of ordering the cereal, and they have to be either low to high or high to low. We have 7 permutations that I could order the cereal, meaning I could there could be 5 options for the first cereal, 4 options for the second cereal, 3, 2, 1. And that's just a factorial of 5 factorial, the ways that you could put 5 cereals together. But this one is specific to not just putting 5 cereals together, but also putting them in the order of high to low. So if you think about that process, the number of ways of putting my price from high to low or from low to high, there's only one way that can happen. And then how many possible ways here can we have for my cereal? Well, we have ordering my cereal could be 5 factorial ways, because again, if I think about, here's a representation of each place for cereal. I could put 5 cereals in that first spot, 4, 3, 2, 1. And we looked at this in section 1, and so that's a factorial there. So I have a 1 over 5 factorial, which is 1 over 120. Here's my probability for ordering my cereal from either high to low or low to high. All right, what's the probability that I just happen to have multigrain as the most expensive? Again, the number of most expensive cereals, there's only one of those. Over the total number of cereals. So we have only one that's the most expensive out of the 5. So we have a 1 in 5 probability here that multigrain would be the most expensive. And that could be the same thing for probability that rice or oats or corn is the most expensive. So one of those 5 cereals is going to have to be the most expensive. One of those 5 cereals would have to be the least expensive. Odds. Odds also depend on an equal likelihood of some event occurring. So here we can say that to think about odds, you have the chances in favor of an event happening or the chances against an event happening. So when we talk about odds, we can say odds in favor or odds against an event. Now what's different here are odds do not compare number of outcomes of an event over the total. But instead, compare the number of outcomes of an event over the number of outcomes that are not in that event. And here we can see the two different conditions. We have odds in favor of an event. So odds in favor, let's say odds of event A happening, divided by the odds, or not the odds, but divided by the number of outcomes for event A not happening. That would be odds in favor. Odds against an event would be I don't want the event to happen, divided by how many times the event could happen. And that would be our odds against. So just think of what I want over what I don't want for odds in favor, and think about what I don't want over what I want for odds against. And again, what's important here is that these two numbers, whatever they are, they always add up to the total number of outcomes. All right, let's go check out some of the odds in here. So we have a six-sided standard die, which basically it's a cube. Right, we're familiar with this. What are the following odds of these events happening? Well, the odds in favor of rolling a 6. So the odds in favor of rolling a 6 are going to be equivalent to rolling a 6, number of ways that I can roll a 6, divided by the number of ways of not rolling a 6. Okay, so we have 1 out of 5. One way to roll a 6. 5 ways to not roll a 6. So that would be my odds in favor of getting a 6. It's 1 to 5. So again, paying attention down here, that 5 is not the total number of possibilities on a 6-sided die. That 5 and the 1 in the numerator add up to the total possibilities of a 6-sided die. A little different from probability, so this is not probability here. All right, what about the odds against an odd? So against an odd, we say we don't want an odd over we do want an odd. So how many of the numbers on a 6-sided dice are not odd? Well, you have 2, 4, 6 that are not odd. And then how many of them are odd? There's 1, 3, and 5. So here we have a 1-to-1 odd against getting an odd, not getting an odd on the die. And we can just simplify that. We got in a bag, 6 red, 12 yellow, 9 black marbles. Finding the following here, again, thinking about odds. We could also maybe include some discussion on probability as well. So we have the odds in favor of choosing a red. So generically speaking, we would say we want a red, and compare that to those that are not red. So in this case, we look at the number of red marbles, and there are 6 of them. And then the number of marbles that are not red, we have 12 yellow and 9 black, meaning there are 21. And this becomes a 2-7 odd, 2/7 odd, that we will get a red marble. The odds against getting a black marble would be not black. How many of those are there? Over how many are black? Now we go find the ones that aren't black, which would be our red and our yellow, and there are 18 of those. And the ones that are black are 9. So here we have a 2-to-1 odd, or a 2 of not choosing a black marble. Our second type of probability is experimental. This is what we will do if we have conducted a survey, or perhaps we're looking at historical events. We're doing experiments, something along those lines that allows us to gather data that is now allowing us to do probability that's experimental versus theoretical. Okay, so notice that in the equation here, probability experimental, it looks pretty much the same. We want the number of favorable events, or in this case, number of trials where A occurs, there's our favorable outcome, over our total outcome. So it's the same kind of a setup in terms of a ratio of what I want over the total. Taking a look at our experimental probability. Here we've surveyed a group of individuals. And from that survey, we have compiled the following information here. We have 22 folks that are type O blood type, 21 that are type A, 5 that are type B, and 2 that are type AB. We want to find the experimental probability that a randomly selected donor, out of that group, a randomly selected donor is going to be type O. All right, so we would say the probability for type O, in this case, our experimental probability, would be the number of type O persons over the total number of persons. And we have 22 type O's, and there are a total of 50, I believe, people in this random sample. And so we get then 11 over 25 would be my probability that it's a type O candidate. Grades on a test, broken down. Again, this would be data that is collected, so we're experimental, not theoretical here. 10 A's, 14 B's, 8 C's, 4 D's, 2 F's. Find the probability that a student has at least, so you got to pay attention to the phrase, at least a C. It's not asking us to find the probability that you will get a C. We want to have probability of at least a C, or another way to think of it, C or better. So this would really mean I want the number of A, B's, or C's, not or, but and. I want the number of A, B, and C grades over the total number of grades. So we have 10 and 14 and 8, so 24 and 8 is 32 out of 38 total grades. And then, let's see, we get 16 over 19, 24 and 8, 32, 36, 38. Yeah. 16 over 19 would be the probability that we have at least a C. Geometric probability deals with the probability of falling into some category of shape, and could be also related to length of a side of a figure, the area of a figure, or the volume of a figure. And these are geometric because we're dealing with shapes of some sort. You could have, like in an archery competition, you have your target that has a bunch of concentric circles, and you could say, what's the probability that you would land in the bullseye of that target? Well, that's a geometric probability, and how it would be calculated would be I have my circles. So here's the outer circle of the target, and then there's the next one, and then there's the next one, let's say. And we want to know what's the probability that I'm going to land in the bullseye. If I wanted to find that probability, I would have to know the area of the bullseye. then I would simply take that area and divide it by the area of the target. And there's my probability, geometrically speaking. So that's what we're going to do here for this next shape. Find the probability that should I have created this really funky target here for arrows, or maybe for darts, as in this case. What's the probability that if I threw a dart, it would land in a given triangle? So I got a couple different options for my triangles, and so I need to go back and recall all my formulas. So area of a triangle is 1/2 the base of height, which means for this guy, it's 1/2 of 3 times 4, or 6 inches squared. And over here, this area would be 1/2 of 40, or 20 inches squared. And once again, this one has 6 inches squared. So those three would make up the area of hitting a triangle. And then you've got what would be the target itself. Right? You have this large rectangle, which is 10 times 440. So the probability of hitting a triangle is equal to the area of a triangle divided by the area of this rectangle. So we already know our area of our triangles. We have 6 plus another 6 plus 20 inches squared, and the area of our rectangle is 10 times 40, or 400. So we get 32 over 400, and that becomes 2/25, I believe. That would be the chances, the probability that I would land in a triangle if I were to throw a dart at that large target there. All right, so geometric probability.